Well, strictly speaking, what I'm going to tell in this particular video is not always necessary, but sometimes it can improve your model. It not improve your model. That's the wrong way to say that. But it can make your model more interpretable and somehow more stable. So let's recall the data set of people, right? So remember that I have 12 different variables, and all these variables, they have different nature. We have IQ, which is measured by making a test. We have height of people in centimeters. We have weight of people in kilograms, and so on and so forth. And this box plot shows you the variation of the values, although I actually should not make this box plot because all these variables have different units. So I cannot make any title for this axis, right? Because this is variation of liters of beer per year, and this is, for example, centimeters of height, right? I cannot show liters of beer and centimeters of height in the same plot. Also, I did it, but it's nonsense. It's just to show you the variation. You can see that some variables vary a lot, some variables vary a little. I didn't include income because income varies even more. You remember it's euro per year, and people do not earn 1 or 2 euro per year. People earn thousands of euros, so the variation will be huge. Okay. So that's the problem we have. The predictors, because we have multivariate data set, we have more than one predictor. And now it becomes a problem because predictors have different units, different variation. And also, most of these predictors cannot be zero, and that's why our intercept is not significant, because intercept shows you what happens to y if predictors are zero. But the predictors cannot be zero, so that's why intercept is not significant, right? And this is just an illustration, right? So intercept has no meaning. It's not interpretable. It's because you simply will never get this value. Neither age nor region nor sex cannot be zero, right? And then also you can see that the effect, how big the difference here, is not comparable. You remember age because it's related to years, and region is related to, like it's just a dummy variable, right? So what we need to do, we need to make these variables somehow equal. How? Well, you already know what to do. You learn in block number 1, standard score. Standard score, it's the way to make your variable unitless, right? Or, in fact, it makes all the values in your variable in the same units as standard deviations. So instead of height of people, we will find out how height of this particular person is distanced from the average in standard deviations. So in this case, if we use z-scores instead of x variables, we can standardize all the variables. And because all the variables will have the same units, will have the same variance, it will be unit variance, right? In this case, we can treat them equally. So we can see, we can compare the variables, we can compare the effects. And then we can also get some other benefits. We will see in a minute how. How to compute standardization, how to make standardization? Well, if you know population parameters, you need to subtract average of population and divide the standard deviation of population. But in fact, we don't have population, we have only our sample. So therefore, the standardization can be made by subtracting average of this variable and divide it to standard deviation. However, if I do this for all my variables and people data, you can see I have some strange box plot here and box plot here, right? The other box plot looks fine. You can see that this is average plus minus 1 standard deviation plus minus 2 standard deviations and so on. But these 3 box plots, they look weird. Why? Because they are not numeric. You remember, this is region, is just minus 1 and plus 1. This is sex, is just minus 1 and plus 1. And this is the hair length, also minus 1 and plus 1. So in this case, because it's not numeric variable, it makes no sense to do this standardization. However, what we can do, we can make 0 meaningful. So instead of using minus 1 and plus 1, we can dummify them and have 0 and 1. So we can, instead of minus 1 and plus 1, we can turn them 0 and 1, right? How we can do it? So if this is x variable, right? So what you can do, you can add x plus 1, and it will turn it to 0 and 2, right? And then you divide it to 2. So that will make your variable indeed a categorical variable from minus 1 to plus 1 to 0 and 1, right? So that's called dummification, so to speak. So you make your variable dummy. Okay. If you do that, all your variables will have 0, because 0 means average for numeric values, and 0 means just one of the levels for the dummy variables, right? Moreover, now you can compare the variables because they will be all unitless. Of course, categorical variables will not be expressed in standard deviations. It will be just 0 and 1. But you can think they're just one piece, right? So one item in this case. One item for numeric variable will be standard deviation, and one item for categorical variable is just a distance between two categories. Okay. So what you see here, it's a new model which I made using these standardized and dummified variables. And now you can see a difference, right? So first of all, the biggest difference is that now intercept is different and it's significant. And the age also different and significant. The region is different. All these effects are different. Why? Because we have used different scale, right? How to interpret these values in this case? Well, apparently this is the model and this is the interpretation. Well, let's interpret this value. When income is equal to this value, when age is 0, when region is 0, and when sex is 0. And to remember, 0 now for the categorical variables, it's replacement of -1. So this is male, this is Mediterranean, and this is just average age, right? And average age, in our case, average age is 34.4 years. So this is the average of all years values I have. So the interpretation is following. If we have a male person from Scandinavia, so it's not Mediterranean, it's Scandinavian, right? From Scandinavia, right? Of age 34.4 years, that's average age. This person, or if you have more than just one person, right? So if you have several ones, then average salary of these persons will be, and I keep making this mistake, it's euro, of course, per year. Okay. So this will be the average salary of this person. That's the meaning of intercept now. So now intercept has a meaning, right? Then the second, people from Mediterranean region, when it's 1, earn by 7,232.5, again, euro per year. I don't know why I make this mistake. Less. Again, now you can see this is the number. Less because it's minus, it's negative. So when you go from 0 to 1, your salary goes by -7 drop, right? So it get drop by -7,000. And if you recall the previous case, you will find out that this is exactly the doubled regression coefficients that we had when we had -1 and +1. Okay. And then similarly, female individuals earn by 350 euro per year less. Okay. So that's it. Now your model is more interpretable at some point, right? And then age, right? So age, change in age by 1 standard deviation, which is 9.5 years, change salary by 7,000 kroner. So in this case, the interpretation is a little bit more difficult, right? So now you do not operate by years, you operate by standard deviations. It has cons and pros, we will discuss them in a minute. Okay. So this is just to compare two models. These are original predictors without any standardization. And these predictors are standardized and dummified, is what you have seen in the previous slide. So this is the models. And look, if you look at the summary, the models are identical. The standard error is the same. R squared, adjusted R squared, the same, right? So everything is the same except regression coefficients. Moreover, you can see that for example, the t-score for age is the same. The t-score for the region is the same. The t-score for the sex is the same. Only this is different because now intercept is meaningful, right? So actually, standardization of predictors doesn't change the quality of your model. It changes only interpretability of your model. So now the interpretability of regression coefficients is a bit better. Also, it makes your intercept meaningful, but it doesn't change the quality of your model. The prediction quality is still the same. And that's a good sign, right? This is the regression coefficients plot. This is what we had before. You can see that now, in this case, it's not interpretable. You can see also standard errors vary quite a lot. The confidence intervals vary quite a lot. But in this case, you can see the confidence intervals are comparable and the effects are comparable. You can see that one standard deviation of age has almost the same effect as just two different regions, right? So the effects are comparable in this case. Of course, you need to keep in mind that this is effect not for 1 year, it's for one standard deviation. Okay. So that's what standardization is. That's the benefits of using standardized values. Now, actually, there is a price to pay, right? So in this case, you need to do additional coding. For example, if you don't standardize values, you just use them as is. In this case, look, first of all, I dummified the variable, so I turned from -1 to +1, right? I put this to 0 and 1. I just take all columns with sex values. It's -1, +1. At 1, it will turn them from 0 to 2, and then I divide it to 2, it will turn them from 0 to 1. Then I do the same for region, dumbify the region, so I make this region from 0 to 1. And then you can see that this is standardization. I take all h values from this column, calculate average of them, and subtract the average, right? So this is x minus m, and then divide it to standard deviation. So this is now z-scores. So this is z-scores. And actually this is also, it's z-score for region. No, for region it's the same, for h it's z-score, right? So this is the price to pay. So you have to standardize manually first. If you have many variables, R has a function, it's called scale, which standardized all your variables in your data frame. But in this case, you can use it only if you don't have any dummy variables, for example. What else? There is a workaround. There is something in between. So instead of standardization, you can use mean centering. Remember, standardization is when you take a variable, subtract average, and divide to standard deviation. But that changes also the units. It makes it unitless. But what you can do, you can just subtract average. If you subtract average, your variable will have 0. It's exactly the average, right? So this new transformed variable will have 0. So it will make your intercept meaningful, but you do not change the units. So it means that you still can interpret, for example, age as years. That's the two models I made. Look, this is standardized and dummified model. So you can see that all these values here. And this is only centered. So age is centered, but region and sex are dummified. You can see this is the same. These are the same. The only difference I have, it's the regression coefficient. So now I turn back to 1 year, per 1 year instead of per 1 standard deviation. So that, from my point of view, that makes model in this particular case a little bit more interpretable. Which way to use? Standardized to just center? It's up to you. It depends on the case. Sometimes standardization is better, especially if you have many variables of different units. Sometimes centering will do the job. Okay. But in any case, it's a good idea to use centering or standardization if you have many x variables. This is just to illustrate. Here I have x minus average and divide to standard deviation. Here I have only x minus average. This is how I got this model. Standardization and centering, they have another benefit. They must be used when you have interaction in your model. That's something we will discuss later. But it's good to know that this transformation exists and use it when it's necessary. In the next video, we will talk about how to visualize your models.